We can continue with the sine y equals sine x function, and instead of doing a linear approximation where we got 0.3, we can do a cubic approximation by getting the third p3 of the cubic polynomial. So to do that, we're gonna first start with our functions and our derivatives. So sine x, cos x, negative sine x, negative cos x. This becomes positive sine x again, and then positive cos x. So when we evaluate these, well, sine of 0, we're going to evaluate them at the center, which is x equals 0. And since sine of 0 is 0, we're just going to get 0 for these terms. All the sine terms just end up being 0. The cosine terms, well, cosine of 0 is just 1, but it will alternate between positive 1, and since we go from positive cos to negative cos, we get negative 1, and then our fifth n equals 5 gives us our an value of 1. Okay, oops, I should really write this properly. This is going to be 1 over 1 factorial. This is 0 over 2 factorial. This is negative 1 over 3 factorial. This is 0 over 4 factorial. And this is 1 over 5 factorial. So when we work out P5, we're going to use the 0 term, which is going to be 0, plus the next term is going to be 1 over 1 factorial, x to the power 1, or x minus 0 to the power 1. It's going to be minus 0 minus 1 over 3 factorial, x minus 0 to the power of 3. Okay, so that represents our term. So I'm just going to simplify this. This is really just going to end up being x minus x cubed over 3 factorial. And if I want to work that out, I'm going to get at 0.3, this is where I'm evaluating that then. This is my approximation. 0.3 is for x minus 0.3 cubed over 3 factorial. And when I plug that into my calculator and I calculate this, I get 0.2955. So if you recall, when we actually calculated this on our calculator, we got 0.295520. Up to the fourth decimal place, we have accuracy. That's only with two terms or up to n equals 3. So we can then set up our Taylor polynomial, or our fifth degree approximation formula. Is going to be 0 plus 1 over 1 factorial, x to the power 1, minus 0 minus 1 over 3 factorial, x cubed, plus 0 plus 1 over 5 factorial, x to the power of 5. Okay, simplifying this, 0 plus, I'm going to leave out the zeros here. We're going to end up with just 1x minus x cubed over 3 factorial plus x to the power 5 over 5 factorial. Okay, so then we're going to work that out. So we're going to plug in 0.3 into this equation, and in our calculator it's kind of easy because we're just going to add the last term. Okay, this is going to be over 3 factorial cubed plus x to the power 5 over 5 factorial. We get 0.3 minus 0.3 cubed plus 0.3 to the power 5. And as we plug that all in, we get 0.2955 20 2025. And looking back at the actual value, we end up with quite a bit of accuracy because up to the 5th decimal place, we have an accurate calculation. So this is our third and fifth degree polynomials. Here, if we take a look at the picture of this, when we take a look at the cubic approximation, look how close that is. This is the actual picture, and it's really indecipherable at x equals 3. There's 4 decimal places of accuracy already at the third degree polynomial. And if we actually work it out on our calculator, which is basically taking an infinite sum, our calculator is doing that. It's taking it to a higher power of n to get a lot of accuracy, but essentially we can get quite a bit of accuracy with very few terms. And this is going from basically linear approximation, which is kind of close, to a cubic, which is really close, to a 5th degree, which is even closer. And we can just keep on adding terms to increase the accuracy of all these approximations.